in fish health management. Fish must live in water. It's your responsibility to make sure that the water doesn't become polluted. More fish become sick because of poor water quality than from any other cause. Sometimes it can be so bad it kills the fish all by itself. If your fish look nice the night before and you find them all dead in the morning, it was something wrong with the water that did it. More often, poor water quality lowers the fish's immune response, and they end up with some other disease, which is then blamed. We all too quickly end up treating for parasites or bacteria instead of checking the water. Good water quality management will do more for keeping your fish healthy and strong than anything else you can do. In water quality management, most problems are virtually invisible. Also, if your water is murky or off color, it may mean that you have a problem, but not necessarily. This is why water quality test kits are so important. A good fish health person will first measure the major parameters with a test kit. Because of the diversity of fish and the water from which they come, we can't cover in any detail all of the different parameters for individual species. However, we can talk about the major concerns which are universal to healthy fish. Let's talk for a moment about fresh versus salt water. There's the obvious difference in salt content. Seawater is 33 parts per thousand salt, and fresh water may be measured in parts per million. In between, we have brackish water, a mixture of salt and fresh water. Throughout the world, fresh and brackish water varies considerably, depending upon the climate and soil types. Seasonal fluctuations in temperature and wet and dry seasons are also common. In contrast, the tropical oceans are relatively stable environments throughout the year, with only slight changes occurring over a much longer time frame. This is why many freshwater and brackish water fish tolerate change better than their saltwater counterparts. Saltwater systems require greater attention to maintaining a stable environment that duplicates nature's. The other major concerns of water quality are the same no matter how much salt is in the water. Temperature is crucial to fish since they are cold-blooded. Temperature controls the speed which the fish's systems operate at. Raise the temperature and the fish's entire systems will start speeding up. Lower it and their systems will slow down. Maintaining a constant temperature of 75 to 80 degrees Fahrenheit will be your best bet. Heaters are available in different sizes and designs and are rated in watts. When raising the temperature, be careful. Don't crank the heater up and walk away. Slowly raise the temperature in small increments. Periodically check the temperature. Heaters are not foolproof. A thermometer is an essential part of your water quality test kit. pH, hardness, and alkalinity are often confused. pH is the negative logarithm of the hydrogen ion concentration in water. It's measured on a scale with 7 being neutral. Anything below 7 is considered acidic, and anything above 7 is basic. For our purposes, we need to know that pH strongly affects the activity of a lot of chemicals in water, which in turn affects the fish. Hardness is a measure of the dissolved earth metals in water, most notably magnesium and calcium. Hardness is measured in parts per million, which is the same as milligrams per liter. Calcium is important as it is absorbed to form bones and teeth and also gives egg strength. Alkalinity is a measure of the dissolved bases in the water. The most important ones for our purposes are the carbonates, which make up the primary buffering system in most water. Alkalinity is also measured in parts per million. When water passes through soils rich in organic deposits, such as rotting leaves and vegetation, the pH, hardness, and alkalinity are all low. When water passes through limestone or dolomite, the pH, hardness, and alkalinity will all be high. In the oceans, with all of the dissolved salts and the coral formations, all of these parameters are high. Your source for water will determine the beginning properties in your tank, but the long-term conditions will also affect pH, hardness, and alkalinity. Using crushed coral, limestone, or dolomite in your system will elevate and stabilize all of these parameters. If you use just gravel or sand and let the organics build up in the tank, they will all drop. This is a common problem in water quality management. A neutral pH, 7, and hardness and alkalinity between 20 and 200 parts per million will be fine for most fresh and brackish water fish. However, in certain cases, such as breeding fish or keeping highly specialized fish, you may want to lower or raise these parameters. To lower them, the easiest way is to use a water softener or a reverse osmosis filter. Another method is to filter the water through a bed of peat, simulating the effects of water draining through rich soil. The downside is that this will darken the water over time due to the tannins in the peat. To raise these parameters, use crushed coral, limestone, or dolomite gravel in the bottom of the tank or in your filter. In saltwater tanks, it's extremely important to make sure that these parameters do not drop over time. Marine fish require very stable, relatively high values for all of them. A pH of 8.5 and total alkalinity and hardness over 250 parts per million is needed. pH, hardness, and alkalinity are all invisible and should be checked with a test kit whenever you have a health problem. Carbon dioxide is a dissolved gas in water and a main byproduct of respiration. The blood carries oxygen to the muscles and tissues, and carbon dioxide is carried out. Carbon dioxide levels should remain fairly low and constant in our systems. Overfeeding and poor filtration can both increase carbon dioxide levels, which causes two major problems. First, it makes it harder for the gills to absorb oxygen, and if carbon dioxide is high, oxygen is usually at its lowest. Also, carbon dioxide in water acts as an acid. And this is where we tie some things together. Limestone is calcium carbonate. Dolomite is a mixture of calcium and magnesium carbonates. They dissolve, giving us calcium and magnesium, which add to the hardness, and carbonates, which provide much of the alkalinity. The carbonates react with carbon dioxide, forming a carbonate cycle. This carbonate cycle keeps the dissolved carbon dioxide levels down, which keeps the pH from dropping. This is why we sometimes confuse the terms hardness, alkalinity, and pH. They are closely related and have a lot of interaction with each other, especially when carbon dioxide is added to the equation. Nitrogen is found in proteins, a major part of fish feeds. As we feed fish, we add nitrogen to their bodies. Some is excreted as waste into the same environment in which they must live. This waste is toxic, so it's important never to let it build up. Ammonium nitrogen is one of the main forms of waste from a fish and is primarily passed across the gill membranes. Many organic substances, such as uneaten fish food and feces, also produce ammonia as they are broken down. If ammonia builds up in the water, the fish has a hard time passing it out of the gills. The tips of the gill filaments show areas of hemorrhaging, and when severe, Infection by other disease agents will soon follow. pH and temperature affect ammonia, with high levels of either increasing the toxicity. Ammonia kills more fish than any other cause. It is virtually undetectable to the eyes or the nose at levels which may be toxic to your fish. Concentrations as low as half a part per million can harm your fish, especially if the pH is high. Fortunately, there are ammonia test kits available that can measure very small amounts of ammonia in water. Different fish can tolerate different levels of ammonia. So for our purposes, instead of looking for a certain level to be alarmed with, understand that any ammonia in the water is a concern. It's an indication that something may be wrong with your management. Nitrites are the biological breakdown product of ammonia. Bacteria found on the filter and other surfaces of a tank are responsible for this process. Nitrites are also toxic to fish at low concentrations. Nitrite replaces oxygen on the hemoglobin in the blood, causing anemia. Fortunately, another group of bacteria transform nitrite to nitrate, which is non-toxic to fish, except at very high levels. The main place where nitrates are concerned is in a marine tank, especially if there are invertebrates being kept with the fish. Water changes are the safest and most effective way to eliminate nitrates. In a well-established, healthy system, this process, known as nitrification, is extremely efficient and works very quickly. As soon as ammonia is produced, it should be transformed to nitrite, which is then immediately transformed to nitrate. In a new tank, expect a rise in ammonia, followed by a rise in nitrite as the ammonia drops, and a rise in nitrate as the nitrite drops. These ups and downs are in direct response to the establishment of the bacteria which are involved in the process. The only time you should accept any significant level of ammonia or nitrite is in a new tank. So what do you do when you measure any ammonia or nitrite in an established system? Immediately change the water, and also stop feeding. This will remove any ammonia or nitrite in the system, and also will stop the addition of a lot of the new ammonia. There are products on the market which absorb ammonia or change it to a non-toxic form. However, none of these will solve the cause of the problem, so you still need to look for a more permanent solution. Watch out for overfeeding. Make sure that you have adequate biological filtration, and above all, measure the ammonia and nitrite whenever you see a problem with your fish's health. The best long-term prevention is to keep your biological filters healthy and never overfeed your fish. A biological filter requires 2 to 6 weeks to fully develop the bacteria needed, so don't expect for one to work before then. Also, many chemicals used to treat diseases may harm this bacteria. Biological filters are living communities. Keep everything clean, but remember that too clean can be a problem as well. If you completely change the filter media, or if you vigorously wash the media, you are eliminating almost all of the bacteria. Also, just like fish, the bacteria in the filter need oxygen. So the more oxygen present, the healthier they will be. Because fish feed is the source of the nitrogen, overfeeding will overload your biological filter's capabilities, and this is the most common cause of high ammonia or nitrite concentrations. Fish breathe oxygen, which is dissolved in the water. Oxygen is measured in parts per million, or percent saturation. Saturation is the point where water contains as much dissolved oxygen as possible under existing temperature and pressure. Cold water holds more oxygen than hot water, and fresh water holds more than salt water. If you have a way of testing oxygen, get a table that will show you saturation levels for different salinities and temperatures. All of our water should be saturated with oxygen. Just like high ammonia, there are varying levels of low oxygen which certain fish can tolerate. Therefore, it's not really safe to set some arbitrary level of low oxygen for your system. Basically, all of our systems should be saturated with oxygen, and anything less is some indication that our management may be flawed. Getting saturation of oxygen in water is fairly simple and depends on just a few things. First of all, there is the amount of fish that we're trying to keep in the system. If you have too many fish, you can use up all of the oxygen faster than you can put it in. Related to this, but more important, is the amount of food going into the system. Remember, the system will develop a whole community of bacteria which is breaking down the ammonia and other waste created by the feed, and that these bacteria use oxygen. The more waste, the more oxygen used. Most oxygen depletion problems occur because there are too many bacteria in the system, not too many fish. Aeration is how we can put more oxygen into the water than nature will. The most common method is to use an air pump. As the air rises through the water, it adds some oxygen. However, the primary exchange of oxygen takes place at the surface as the bubbles break the surface tension, making gas exchange more efficient. Power filters produce the same result as they spray water back in the tank at the surface, so you may not need an air pump at all. Wet-dry filters are also excellent aerators. As the water trickles through the media, it picks up oxygen from the air. Remember that the most important things are that you don't overcrowd the system and that you don't overfeed the system. Just like everything else in fish health management, the best remedy is going to be prevention. Finally, let's talk a bit about pollutants and poisons that come from outside our systems. Remember, water is the universal solvent, which means that a lot of chemicals will dissolve in it. You need to be extremely careful when using even common household chemicals near the tank, as many will kill fish at extremely low concentrations. Heavy metals such as lead, zinc, and copper can be toxic, and of course, you must be especially careful with insecticides. The most common pollutant killing fish is chlorine coming from tap water. Most cities add chlorine or chloramine, a compound containing chlorine and ammonia, to keep the water free of bacteria. Chloramine adds a twist because if you remove the chlorine, you still have the ammonia. There are products available which remove both of these instantly. You can wait a day for the chlorine to dissipate on its own, and then use your biological filter to remove the ammonia. But it is much easier to just add a commercial chloramine remover. Different cities use different amounts of chlorine and chloramine, so make sure to test the levels before you put fish in the systems. One last word on poisons and pollutants. They are often blamed when they had nothing to do with the problem. Always look for another explanation, such as high ammonia. Using an unknown chemical as a scapegoat is easy, but it often ignores that the problem was really a result of poor management. There are other parameters of water quality which may or may not be important to you as a fish health manager, but if you learn to deal with the main ones we've discussed, you will prevent most diseases from ever occurring. Maintaining good water quality is relatively easy if we don't overcrowd our systems, don't overfeed, make regular water changes, and keep our biological filters in good health. Most of the problems are invisible, so we need to use test kits to check them out. Before you start blaming a disease agent, make sure that the water is in good shape.
You'd be surprised how often something as simple as a water change or just backing off the feed will solve the problem. Fish have a good immune system, but this system is compromised whenever the water quality drops. Keep your water in good shape, and your fish will usually take care of the rest for you.